Self-adjoint ordinary differential equations. So in the last class, we discussed about solutions of ordinary differential equation. For a second order differential equations, we find out two independent solutions and there is no third solution. Now we will discuss the general property of the solution. There is a close analog between this concept and the concept in the chapter matrix. Functions play the role of vectors. In the case of matrices, there are vectors. Here in the case of a second order differential equations, the functions play the role of vectors. There is a relationship between these second order differential equations and matrix. Linear operators plays the role of matrix and diagonalization of matrix corresponds to the solution of ordinary differential equation defined by self-adjoint operator. So what is a self-adjoint operator? Self-adjoint operator is nothing but the Hermitian operator of matrix. Hermitian operator, otherwise called a self-adjoint operator. Normally this representation indicate bra vector and this indicate a ket vector. So in the bracket notation, u l u will give you u into lu, that is equal to integral between the limit a to b u of x l u of x dx. Here in this case L is the operator, differential operator. Here L is taken as differential operator. So we know that the general form of a linear second order differential equation is L of u is equal to P0 of x d square u by dx square plus P1 of x du by dx plus P2 of x into u of x. For P0, P1, P2 are real functions of x and over the region of interest a between the limits a and b. In general, we know that the form of second order differential equation is d square y by dx square plus p of x dy by dx plus q of x y is equal to L of x. L is the differential equation, the operator, L operator, differential operator. We already discussed about this operator. So here when we compare these two equations, if we write the equation in this form, we can divide this equation by P0 and we can equate these two forms. Here P of x is nothing but P1 of x divided by P0 of x. Q of x is given by P2 of x divided by P0 of x. So we can make these two equations in a similar form. For that we have to divide this by P0 of x. So we will get the relation P of x as P1 of x divided by P0 of x and Q of x is equal to P2 of x divided by P0 of x. Here P0 of x must not vanish between the limit a and b. The interval a and b should be chosen in such a way that no singular point in the interior of this interval. So there should not be any singular point between the interval a and b. So that is the condition for the existence of this relation. So in the bracket notation, u l u is equal to between the limit a to b, u into, we have to write the form of L. L is nothing but P0 u double dash plus P1 u dash is an operator, differential operator, plus P2 u dx. So this can be written as u P0 u double dash plus u P1 u dash plus u P2 u dx. So in order to now we are going to integrate this equation by the rule of integration by parts. We know that integral u dv is equal to uv minus integral du dot v. So you have to integrate this equation twice, then this u double dash will be integrate first. In first integration you will get u dash from this equation, then after integrating you will get u from this equation. So this can be written as, so when we are going to integrate this equation, be careful while integrating. There is a chance of k mistakes while integration. So u lu is equal to u p0 first function. This is the first function, so that's why we are put it in a bracket, and this is taken as the second function. So u p1 so when we integrate this, you will get u p0 first function into integral of the second. When you integrate u double dash, you will get u dash between the limit a and b minus integral of differential of the first function. Here u p0 is the first function, so it's differential, into integral of the second, u double dash, integrate, you will get u dash into dx plus the second term. Similarly, first function into integral of the second, then you will get u p1, u between the limit a and b minus integral of differential of the first. So we have to put a dash d by dx. So u p1 dash into integral of the second. When you integrate this, u dash u dx. Okay, plus the third function. Third function is put as such, plus integral u p2 u dx. So when we will integrate it once again, so you will get this equation, first equation as such, first term as such, u p0 u dash between the limit a and b. Second function, this is a dash term. Now we will integrate this equation. You will get first function into integral of the second. When you integrate u dash, you will get u. So a constant term will arise, minus u p0 dash u between the limit a and b minus of integral into differential of the first into integral of the second. When the differential of the first means u p0 double dash integral of the second u dx, and this term remains as such. And when we integrate this term, you will get, and also we put that term as such here, u p1 dash u dx, because our aim is to integrate u dash. Okay, in order to by integrating u dash, you will get u. Okay, so this is the equation, third term. Last two terms are remains as such. So after doing this operation, you will get an equation this for u l u. Now we are going to arrange these terms. Okay. When we do this calculation, you know u p0 dash, after that means d by dx of u p0, that is d by dx of u p0 is u p0 dash. When we do the differentiation, you will get two terms, u p0 dash u and u dash p0 u. So there is a minus sign common here. So the second term and the last term will cancel. Here u p0 u dash between the limit a and b. Here also minus. The second term is u dash p0 term will also come after differentiating this equation. So that will cancel and only one term exists here. So u into lu, you will get u of x p1 minus p0 dash u between the limit a and b plus a to b d square by dx square p0u minus d by dx of p1u plus p2u into u dx. So when we do this differentiation, d square by dx square p0u, you will get d square by dx square p0u, that is equal to d by dx of p0u. So you will get d by dx of p0 dash u plus u dash p0, that is equal to u p0 double dash 2. When we do this, p0 dash u dash here also u dash p0 dash. So you will get 2 u dash p0 dash plus last term p0 u double dash. So this will become ulu is equal to u of x p1 minus p0 dash u of x between the limit a and b integral u into p0 double dash u plus 2 u dash p0 dash u plus p0 u double dash u plus the last term, that is minus p0 dash u minus here there is a minus sign. So if we put a bracket here, we can write here as plus. This is p1 u dash u plus integral p2 uu dx. Comparing the equation 2 and 3, so you will get this is equation 2, that is ulu is equal to integral a to b u p0 u double dash plus p1 u dash plus p2 u dx, and this can be written, so this can be written in this way. So when you compare each term, you will get an equation like this. On comparing or equating equal integral terms, you will get u into bracket u p0 double dash minus p1 dash plus 2u p0 dash minus p1 u dash is equal to 0, or this will equal to 0 when p0 dash is equal to p1, or when we once again differentiate this, you will get p0 double dash is equal to p1 dash. So the constant term in the equation is also vanish. So this is the constant term in the equation. So in this equation, this term will vanish because we prove that p1 minus p0 dash should be equal to 0, or p1 is equal to p0 dash. So this equation is vanished, and you will get the equation as L of u is equal to d square by dx square p0 of u minus d by dx of p1 of u plus p2 of u. Okay, so in matrix, Hermitian matrix is called the self-adjoint matrix. That is, self-adjoint means nothing but the complex conjugate transpose of a matrix. So L of u is equal to p0 u double dash plus 2 p0 dash minus p1 u dash plus p0 double dash minus p1 dash plus p2 u. When we do this differentiation, you will get this equation as L of u is equal to, and we are rearranging the terms corresponding to u double dash, u dash and u. You will get Lu as p0 u double dash plus 2 p0 dash minus p1 into u dash plus p0 double dash minus p1 dash plus p2 into u. Okay, for a necessary and sufficient condition for A second order linear differential equation should be a self-adjoint equation is that this ULU should be equal to ULUU. ഇങ്ങനെ ഇതാണ് ഈ കണ്ടീഷൻ സാറ്റിസ്ഫൈ ചെയ്താൽ മാത്രമേ സെക്കൻഡ് ഓർഡർ ഡിഫറൻഷ്യൽ ഇക്വേഷൻസ് സെൽഫ് അഡ്ജോയിന്റ് ഇക്വേഷൻ ആക്കാൻ പറ്റുള്ളൂ. അങ്ങനെ ഈ കണ്ടീഷൻ ഇങ്ങനെ ഒരു ഇക്വേഷൻ ഉണ്ടെങ്കിൽ നമ്മൾ സെക്കൻഡ് ഓർഡർ ഡിഫറൻഷ്യൽ ഇക്വേഷൻ തന്നാൽ നമ്മൾ പറഞ്ഞു ആദ്യം കണ്ടീഷൻ പറഞ്ഞു P1 ഓഫ് എക്സ് എന്ന് പറയുന്നത് P0 ഡാഷ് ഓഫ് എക്സ് ആയാൽ മാത്രമേ ആ ഇക്വേഷൻ ഒരു സെൽഫ് അഡ്ജോയിന്റ് ഇക്വേഷൻ ആയി മാറുകയുള്ളൂ. അപ്പോൾ സെക്കൻഡ് ഓർഡർ ഡിഫറൻഷ്യൽ ഇക്വേഷൻ കിട്ടിക്കഴിഞ്ഞാൽ അതിൽ P1 ഓഫ് എക്സ് ഇസിക്കൽ ടു P0 ഡാഷ് ഓഫ് എക്സ് ആണോ എന്ന് ചെക്ക് ചെയ്യുക. ആണെങ്കിൽ ദാറ്റ് ഇക്വേഷൻ ഇസ് എ സെൽഫ് അഡ്ജോയിന്റ് ഇക്വേഷൻ. അല്ലെങ്കിൽ നമുക്ക് ആ ഇക്വേഷനെ സെൽഫ് അഡ്ജോയിന്റ് ഇക്വേഷൻ ആക്കാൻ പറ്റും. അതിൻ്റെ മെത്തേഡ് നമ്മൾ പറയുന്നുണ്ട്. ഒരു സെൽഫ് അഡ്ജോയിന്റ് അല്ലാത്ത ഇക്വേഷനെ ഹൗ ക്യാൻ വി മേക്ക് ദിസ് ഇക്വേഷൻ ഇൻ ടു എ സെൽഫ് അഡ്ജോയിന്റ് ഇക്വേഷൻസ്, അതിൻ്റെ കണ്ടീഷൻസും കൂടിയാണ് നമ്മൾ ഡിസ്കസ് ചെയ്യുന്നത്. അപ്പോൾ നെസസറി ആൻഡ് സഫീഷ്യൻറ്റ് കണ്ടീഷൻ ഫോർ എ സെക്കൻഡ് ഓർഡർ ഡിഫറൻഷ്യൽ ഇക്വേഷൻ ടു ബി എ സെൽഫ് അഡ്ജോയിന്റ് ഇക്വേഷൻ ഇസ് ദാറ്റ് P1 of x should be equal to P0 dash of x. Okay. L bar of u should be equal to L of u. L bar is self-adjoint operator of L of u. So, if both are equal, if L of u is equal to L bar of u, we can say that this is a self-adjoint operator. When we apply the condition P1 of x is equal to P0 dash, this equation will reduce into L of u is equal to L dash of or L bar of u is equal to L of u, that is equal to d by dx of p of x dy by dx plus q of x into y of q into y of x. Okay, actually you can put the parameter here. I put the parameter as u. By mistake I write here as pi. Okay, anyway, L bar of u is equal to L of u is equal to d by dx of p of x into du by dx, here not y, du by dx plus q of x u of x. So that is the correct form. Okay, so here what happened is, here P0 is replaced by a p of x, and this P2 of x is replaced by q of x. Here we replace P1 of x by P0 dash of x. Okay, so when we do this, this is the necessary and sufficient condition for a operator to be self-adjoint. So this is an equation for a self-adjoint or differential operator. L dash of or L bar of u is equal to L of u, that is equal to d by dx of p of x dy by d or du by dx plus q of x u of x. Okay. Normally the linear harmonic oscillator and Legendre equations are self-adjoint. We can check whether that equation is a self-adjoint or not by putting P0 dash of x is equal to P1 of x. Okay. But ordinary differential equations like Legendre equations and Hermite equations are not self-adjoint. So how can we convert a non-self-adjoint equation where P0 dash of x not equal to P1 of x into a self-adjoint form? This can be done by multiplying L by 1 by P0 of x e raised to integral P1 of, here the limit from 0 to x, P1 of t dt divided by P0 of t. Okay. Here the parameter, varying parameter is t. When you do this calculation and put the limit, you will get this term in terms of x. So there is no problem for putting an variable t here. Okay. After integration and putting the limit, you will get this in terms of x. So the method to convert a non-self-adjoint operator into a self-adjoint operator is multiplying the equation by 1 by P0 of x is to integral P1 of t dt divided by P0 of t. So this, when we multiply L of u by this term, you will get this is equal to 1 by P0 of x e raised to integral P1 of t dt divided by P0 of t. The first term P0 u double dash, second term we have to multiply by 1 by P0 of x e raised to integral P1 of t dt divided by P0 of t. Second term is P1 u dash plus the third term 1 by P0 of x here is to integral P1 of t dt divided by P0 of t into P2 of u. Okay. So this is equal to this P0 term cancels. So the first term containing e raised to integral P1 of t dt divided by P0 of t u double dash plus here P1 by P0 e raised to integral P1 of t dt divided by P0 of t u dash. The last term is P2 divided by P0 e raised to integral P1 of t divided by P0 of t into dt. So we can combine these two equations. That can be combined as d by dx of u dash e raised to integral P1 by P0 dt plus. So when we distribute these two terms after differentiation, you will get these two terms, and the last terms remains as such, that is P2 by P1 e raised to integral P1 divided by P0 dt into u. So this is the self-adjoint form of an operator. So this is the self-adjoint form of an operator. One condition is that P0 is in the denominator. So P0x will not equal to 0 between the limit a and p. Let us consider two problems. So here x square plus y square y double dash plus x y dash plus x square minus n square y is equal to 0. So this is a puzzle equation. Whether we have to check this equation is a self-adjoint or not. So here P0 dash is equal to P1 is the condition for an operator to be self-adjoint. Here P0 is nothing but x square. P0 dash is equal to, so when we differentiate it, you will get it as a 2x. What is P1? P1 is x here. So this is not a self-adjoint operator because P0 dash is equal to 2x and P1 is equal to x. So we have to convert into self-adjoint form by multiplying 1 by P0 of x here is to integral P1 of t divided by P0 of t into dt. So that is equal to P0 of x is nothing but x square, 1 by x square here is to integral t divided by t square into dt. This 1 t and t get cancelled, you will get 1 by t dt. So this is 1 by x square here is to integral 0 to x 1 by t dt. So 1 by x square here is to integral 1 by t dt is nothing but ln x, here is to ln x is nothing but x. So that is equal to x divided by x square. So when 1x cancel, you will get it as a 1 by x. So multiply the whole term by 1 by x, you will get this as x y double dash plus y dash plus x square minus n square by xy is equal to 0. So when we check this equation, so this is a P0 of x is x here. So P0 dash of x is equal to 1. So here is here also P0 dash is equal to 1. So this is this equation become a self-adjoint equation. This is the method to convert a non-self-adjoint equation into self-adjoint equation. So the self-adjoint form of an equation is L of u is equal to L bar of u, that is given by d by dx of p of x du by dx plus q of x u of x is equal to 0. So the equation, that is x y double dash plus y dash plus x square minus n square by xy, that is equal to 0. That is the self-adjoint form of Bessel equation. So this can be written as d by dx of, when we can combine these two terms, d by dx of x du by dx plus x square minus n square by x into, it is u not y is equal to 0. So that is the general. So we obtain the general form of self-adjoint equation. Okay. Next one is Legre equation. It is x d square u by dx square plus 1 by x 1 minus x du by dx plus n u is equal to 0. It is not y, it is u. U is equal to 0. So convert it into self-adjoint form. We know that p0 dash of x is equal to p1 of x for self-adjoint operator. Here p0 of x is x. So what is p0 dash of x? It is 1. It is not equal to p1 of x. It is 1 minus x. So it is not a self-adjoint equation. So we have to convert its self-adjoint equation by multiplying the equation with 1 by p0 of x raised to integral p1 of x divided by p0 of x. First we have to calculate what is its value. So here 1 by p0 of x raised to integral p1 of x by p0 of x is given by, here what is p0 of x is nothing but x. So 1 by x e raised to integral p1 of x, or let us put it in terms of t, another parameter. After integration we can convert it into in the form of x. So p1 of t, what is p1 of t is nothing but 1 by t, and p0 of t is t itself. So 1 minus t by t dt. We have to integrate between the limit 0 to x. Okay, so 1 by x e raised to integral 0 to x. When we split this term, you will get 1 by t minus 1 into dt. So 1 by x e raised to, when we integrate these two terms, integral 1 by t dt become ln of x, and minus dt, integrate between 0 to x, you will get e raised to minus x. So this is nothing but 1 by x e raised to ln of x into e raised to minus x. So that is given by 1 by x. E raised to ln of x is nothing but x e raised to minus x. This x and x get cancelled. You will get this as e raised to minus x. So this multiplying factor is nothing but e raised to minus x. So നമുക്ക് ഇതൊക്കെ ഇതിലെല്ലാ ടേമിലും അതിനെ മൾട്ടിപ്ലൈ ചെയ്യുമ്പോൾ ഈ ഫാക്ടർ കൊണ്ട് നമ്മൾ ഈ ഹോൾ ടേമിനെ മൾട്ടിപ്ലൈ ചെയ്യുമ്പോൾ യു വിൽ ഗെറ്റ് ഇ റീസ് ടു മൈനസ് എക്സ് എക്സ് ഡി സ്ക്വയർ യു ബൈ ഡി എക്സ് സ്ക്വയർ പ്ലസ് ഇ റീസ് ടു മൈനസ് എക്സ് 1 മൈനസ് എക്സ് ഡി വൈ ബൈ ഡി എക്സ് ഇ റീസ് ടു മൈനസ് എക്സ് എൻ വൈ അല്ല എൻ യു ഇസിക്കൽ ടു 0. ആൻഡ് യു എൻ വൈ ചേഞ്ച് ചെയ്തിട്ടുണ്ട്, ഒന്ന് സൂക്ഷിക്കുക. 0 ഏതെങ്കിലും ഒരു പാരാമീറ്ററിൽ ഒന്നുകിൽ യു വിൽ കംപ്ലീറ്റ് ആയത് അല്ലെങ്കിൽ വൈയിൽ കംപ്ലീറ്റ് ആക്കരുത്. ഓക്കെ, ദർ ഈസ് നോ പ്രോബ്ലം ഫോർ ദാറ്റ്. സോ ഹിയർ p0 of, now we will get the equation. When we check this equation for self-adjoint condition, what is p0 of x is nothing but e raised to minus x. When we differentiate this equation, you will get this is equal to here p0 of x is nothing but e raised to minus x into x. There are two terms, multiple of two terms, x into e raised to minus x. When we differentiate this equation, you will get e raised to minus x with one term, then e raised to minus x into minus e raised to minus x into x, second terms. Okay, so that is equal to this e raised to minus x into 1 minus x. When you differentiate this, you will get this term. So that means p0 dash of x is equal to p1 of x. So this equation is a self-adjoint equation. So we convert a non-self-adjoint equation into self-adjoint equation, or operator into non-self-adjoint operator. Okay, this is the method of converting a non-self-adjoint operator into a self-adjoint operator. Eigenfunction and eigenvalues. The eigenfunction and eigenvalues in the case of a self-adjoint operator in Schrodinger equations, we know that h into psi of x is equal to e into psi of x. In ordinary differential equation, the differential operator L is defined by Hermitian h, and eigenvalue become the total energy E of the system. Okay, here instead of h we are using the self adjoint operator L. Okay. A more general form of self adjoint equation is the eigenvalue equations take the more general self adjoint form like this: L into u of x plus lambda w x u of x is equal to 0. This is the eigenvalue equations for self-adjoint operator. So here lambda is the eigenvalue, and u of x, you know that the eigenfunction, and w, here w of x is nothing but the weight function or density function. Normally the w of x is always greater than 0. Okay. For some isolated points, it is w of x is equal to 0. Normally we consider the case where w of x is greater than 0. For a given choice of parameter lambda, a wave function u of x which satisfy the equation L u of x plus lambda w u of x and imposed boundary condition are called eigen functions corresponding to lambda. So what is an eigen function? For a given choice of parameter lambda, the eigen function u lambda which satisfy the equation thus and imposed boundary conditions are called eigen functions corresponding to eigenvalue lambda. So that about eigen function. So the general form of our self-adjoint operator is L of u is equal to d by dx of p of x du by dx plus q of x u of x. So the eigenvalue, we know that eigenvalue equation is nothing but L into u of x plus lambda w of x u of x is equal to 0. Okay, now we are going to substitute for L of u from this equation. Then you will get d by dx of p of x du by dx plus q of x u q of x and we are combining these two terms, q of x here lambda w of x and u of x is a common factor, so we can take outside, that is equal to 0. So let us do some problems. The question is like this: Legendre equation is given by 1 minus x square y double dash minus 2x y dash plus n into n plus 1 y is equal to 0. Show that Legendre equation is a self-adjoint form and weight function w of x is equal to 1 and it is a weighing function. The question is show that this is the self-adjoint equation, also find out the value of w of x or prove that w of x is equal to 1 for Legendre equations. Okay, here when we check for the self-adjoint form of this equation is p0 dash is equal to p1. Here p0 dash is d by dx of 1 minus x square, it is nothing but minus 2x. So here also this minus 2x, so this is minus 1. So this is in the self-adjoint form. Okay. So this equation can be written as this d by dx of 1 minus x square into dy by dx plus n into n plus 1 y is equal to 0. When we differentiate this equation, you will get 1 minus x square taken outside, d square y by dx square. The first term is here, and when we differentiate this, you will get minus. This is a common differential. So when we differentiate these two terms, you will get the first term ആദ്യം കിട്ടി, പിന്നെ രണ്ടാമത്തെ term 1 minus x square. When we differentiate this, you will get minus 2x y dash. So these are equal, same equations. So this is in the. So when we compare this equation with our eigenvalue equation, that is our eigenvalue equation is L of u plus lambda w of x u of x is equal to 0. So when we compare this equation, we will get this w of x is equal to, in this case here, n into n plus 1 into y or u is the last term. So this is the term containing lambda w u of x. Lambda w u of x nothing but n into n plus 1 u. Okay. So this n into n plus 1 is nothing but lambda, and when we check for u of w of x here, w of x value is 1. So here w of x is equal to 1, and lambda is equal to n into n plus 1. In certain books, lambda is given as L into L plus 1 instead of n. Okay, so we will get w of x as 1 and lambda as n into n plus 1 from this equation. So this about the self-adjoint operator and its eigenvalues and eigenfunction.